Hello students, welcome to my YouTube channel Data Sharp. And in the last lecture we were talking about the formulation of the linear programming problem. So we have studied that how we can formulate the problem into LPP in this form, where we can maximize or minimize our objective function subject to certain constraints with the non-negativity constraint. So let us consider certain examples. In the first one, a furniture dealer deals in two items, the tables and the chair. He has $10,000 to invest and a space to store almost 60 pieces. So first of all, whenever we are talking, reading a problem, so in the first line itself, we could figure out that what would be our x1 and x2. So let us consider x1 as the number of items, that is we are talking about the tables. So in this, x1 would be the number of tables and the x2 would be the number of chairs. So let me just write down number of tables, number of chairs. So if I formulate here in the form of a table, or you could easily see that here we are talking about, he has $10,000 to invest. So that means the maximum investment that the dealer is having is $10,000. So a table cost him $500 and a chair is costing $200. He can sell a table at a profit of $50 and a chair at a profit of $15. Assume that he can sell all the items that he buys. Formulate the problem as a LPP so that he can maximize the profit. So what would be our linear programming problem? So the linear programming problem is given by, first of all, the objective function. So we have to maximize our profit. So we always write it as maximize Z. Now, the profit, as we can see here, the table, one table is giving us a profit of $50. So as we are having x1 number of tables, so it would be 50 times x1 plus one chair is giving us a profit of $15. So x2 chairs would be giving us 15 times of x2, subject to the constraints. So the constraint, the first, as he is having the maximum investment of $10,000, so this is 10,000. Now for a table, the cost is 500 for one table. So for x1 tables, it would be 500 times x1. For one chair, the cost is $200. So for x2 chairs, it would be 200 times x2. Also, we are given that the space, the maximum pieces that they can store would be, the maximum pieces that they can store is only 60 pieces, right? So again, only 60 pieces can be stored. So x1 plus x2 would be less than equals to 60, where both should be greater than equal to 0, because the number cannot be negative. So it has to be greater than equal to 0. So this is how we can formulate our problem into LPP. Let's move to the next example. In this, we have a factory produces two products, A and B. So again, we are talking about the two products here. So let x1 be the number of units of the product A and x2 be the number of units of the product B. Each of the product requires 2 hours of molding, 3 hours of grinding, 4 hours of polishing, and for the product B also we are having the same different number of hours. So what we can do here, we can formulate a table. So it would become easy for us to write down the constraints and the objective function. So let me just take here the product then the number of hours of molding, the number of hours for grinding, then polishing, so product A, product B. So let me just take another color pen so that we can easily identify. So I'll quickly write 2 hours of molding, 3 hours of grinding, and 4 hours of polishing. For product B, 4 hours of polishing, 2 hours of grinding, and 2 hours of polishing. Now the molding machine can work for 20 hours. So here the availability, the time availability is also given to us. For the time availability is given to us in hours. So it's 20 hours. For grinding it is 24 hours, and for polishing it is 13 hours. Now the profit is $50 per unit of A and $30 per unit of B. Assuming that the factory can sell all that it produces, formulate the problem as a LPP to maximize the profit. So again, we have to maximize the profit. So now the LPP is given by, first of all, we'll be writing the objective function. So the objective function is maximize Z. So as we have to maximize the profit, so here you can see we are having 50 units per A, 30 units per B. So 50 times X1 plus 30 times X2 subject to the constraints. Now we'll be having 3 different constraints, for one for molding, second for grinding, and third for polishing. So the total number of hours available to us is 20 hours for molding. So it would be less than equal to 20. So this would be 2x1 plus 4 times x2. That's less than equals to 20. Now for the grinding, as you could see, we have 24 hours only. So 3x1 plus 2x2. So 3x1 plus 2x2 is less than equals to 24. Lastly, for the polishing, 4x1 plus 2x2 is less than equals to 13. And with the non-negativity constraints, x1 and x2 must be greater than equal to 0, and obviously they are integers, and that's the non-negativity constraint. So this is how we can formulate our problem into LPP. Now let us talk about the next one, where we are having a manufacturer produces 3 models 1, 2, 3 of a certain product. He uses 2 types of raw materials A and B, of which 4,000 and 6,000 units respectively are available. So the availability that is given to us in this table, we can add that for A the availability is 4,000 and for B it is 6,000. So as we know, whenever we talk about availability, so if I take the number of units of model 1 as x1, for 2 as x2, and 3 as x3, then 2x1 plus 3x2 plus 5x3 would be less than equals to 4,000. So these two becomes our the first 2 constraints, right? So these would be our constraints. So let's move ahead. The labor time for each unit, 1 unit of model 1 is twice that of model 2 and 3 times that of model 3. The entire labor force, that means when you add them all, of the factory can produce the equivalent of 2,500 units of model 1. So we'll be writing it in terms of model 1. A market survey indicates that a minimum demand of the 3 models are these. So the minimum demand of the model is given to us. So in this case, however, the ratios of the number of units produced must be equal to 3:2:5. Assume that the profits per unit is 60, 40 and 100 rupees respectively. Formulate the problem in order to determine the number of units, again with the maximized profit. So let me just write the, let me take the pen. Let x1 be the number of units of model 1, x2 be the number of units for model 2, and x3 would be the number of units for model 3. So when we are formulating the LPP, so LPP is given by, because we have to maximize the profit, so the objective function would be maximize Z. So it was 60, 40 and 100 rupees respectively. So it would be 60x1 plus 40x2 plus 100x3. Subject to the constraints, as I told you, the first two are for the raw materials A and B. So it would be 2x1 plus 3x2 plus 5x3 is less than equals to 4000. Similarly, for the raw material B, it would be 4x1 plus 2x2 plus 7x3 is less than equals to 6000. Now we talk about the labor constraint. So it's twice of the model 2, 3 times of the model 3. So that's happening again and again. So it would be x1 plus 2 times model 2, 3 times model 3, less than equals to 2500. That's the total capacity of the labor hours that we have. Also, we have here that the 3 models, the minimum demand is 500, 500 and 375. So in the ratio of 3:2:5, right, the ratios of the number produced must be equal to this. So it would be 3x1 less than equals to 500, then 2x2 less than equals to 500, and 5x3 less than equals to 375. Lastly, the non-negativity constraints, that x1, x2, x3 all must be greater than equal to 0 and must be integers. So this is how we can formulate this problem. So these 3 problems we discussed about the maximizing profit. So that was our objective function. Now in this particular example, we are having a minimum cost. So that would be our objective function. So let's consider vitamin C and vitamin E are found in 2 different units of fruits, F1 and F2. 1 unit of F1 contains 3 units of vitamin C and 2 units of vitamin E. So now as we could see, the hospital, if we read, hospital wants to purchase such units of fruits of F1 and F2 which supplied to the patients to meet the minimum requirements at minimum cost. So what we'll be assuming here, let x1 be the number of units of F1 fruit, x2 would be the number of units for F2 fruits. So let us create a table quickly. So here for F1 we are talking about the fruits F1 and F2, and this is the vitamin C content, vitamin E content, and we are also talking about the cost. So let me take another color pen. So 3 units of vitamin C and 2 units of vitamin E. We are talking about the fruit one. So 3 units, 2 units. Similarly, for 1 unit of F2, 2 units of vitamin C and 3 units of vitamin E. Now a patient needs the minimum of 30 units of vitamin C. So 30 units are required. So this would be the availability, the requirement of a patient. And vitamin E, they require 20 units. So that's the total that they can, the minimum that they need to have. and then 1 unit of F1 cost 20 rupees, so this is 20 rupees, and 1 unit of F2 cost 25 rupees. So now we can formulate our LPP. So very clearly you could observe here, first of all we have to minimize the cost, so the objective function would be LPP is given by minimum or minimize Z, that is 30 is it, sorry, 20x1 20x1 plus 25x2 subject to the constraints. So now when we are talking about the vitamin C and vitamin E constraints, we could see there are 3 units for F1, so 3x1 plus 2x2, 3x1 plus 2x2 is greater than equal to 30, the minimum requirement that they have. Similarly, 2x1 plus 3x2, this is for F2, vitamin E, sorry, that's greater than equal to 20 units, given x1 and x2 must be greater than equal to 0. So they have to be integers and they must be greater than equal to 0. So these were few examples how you can formulate your problem into a linear programming problem. So we'll be meeting next and in the next lecture we'll be talking about the graphical method. Thank you.